Hello. Hi guys, good morning. Welcome back. So we will see bi-weekly contest 122, problem number 4. Divide an array into sub-arrays with minimum cost 2. It had very less summation because it is actually a hard problem. But as soon as you will see the entire intuition and the solution, you will figure out, it was actually a very medium problem. But again, to come up to it and actually think of in that direction, it's actually tricky. And implementing is also a bit tricky. So yeah, let's start off and see what the problem says. It says, and again, it had a cost of 1 also, which we saw already earlier. It's just very brute force approach. Now, it just says that you are given a 0 indexed array of integers called as nums of length n and 2 positive integers k and dist. And the cost of the array of its first element, which is just okay, say we have just integer array called as nums and we have 2 positive integers k and dist. Dist is the distance, and the cost of an array is the value of the first element. So if I just take any array, now why they're specifically taking any array and just taking the first element? Because in the next part they will actually talk about the sub array. So the cost of that specific sub array is nothing but the first element of that sub array, which is in this case as 1. In this case, it is actually a 3, and so on and so forth. Now, we need to divide this nums into k disjoint continuous subarrays. So that's the reason my k came in picture, because I have to just divide, okay, this is specifically one array, I have divided into k disjoint subarrays, which means if I have this subarray, my k is 3, so I have to say, okay, put it as k equal to 3. Like, put this entire array into 3 partitions, as in 3 buckets or 3 groups, and that will be actually my disjoint subarray. So for sure, what the word means disjoint is that it should not be intersecting, which means 2 subarrays should not be intersecting. Continuous, which means okay, all the elements should for sure come in the final, and subarray is just a part of an array, continuous part of an array. Now everything is done good. Okay, we'll simply divide our entire array into disjoint continuous subarrays of size, like number of such subarrays will be 3, which is k. But the condition is that the distance, okay, this is the first, second, third, right? This is the third. So he says first and last one, the difference in the indexes of the first and the last one. And when I say indexes, I only mean the starting value of the last group, starting value of the first group. So this index difference should be less than equal to distance. This is what the problem is saying. Now let's see that how we will solve it. For sure, brute force may or may not work. Let's see why the brute force will not work. So one thing is for sure that okay, we have k disjoint subarrays. Now for sure, if I am starting off and I want every element to come, so for sure the first group will for sure start off with 1 itself. He can end anywhere, he can end at 1 itself, he can end at 1 3 1 3 2, but I'll say he'll start off with 1 itself for sure, because I cannot skip 1. I will have to take 1 for sure, because I want all the elements to come. It is continuous subarrays. So for sure this 1, which means nums of 0, will for sure be added in your answer. In the output, it will for sure be added, because you remembered I have to break it down to some continuous subarrays, some disjoint continuous subarrays, and I'll take the first element and that I should add my answer. So I'll simply add these in my answer. That is very okay. But what are possible options we can have? So you will see that there can be multiple options. Let's take a very small example. This is a very small example, but we will see this example itself. So for the first group, I can either take 1 element in that first group, or 2 or 3 or 4 or 5. 5 cannot. Why? Because if I take 5, then the remaining space will only be 1. So I could only make 1 more group. Ultimately, remembered, I have to make 3 groups for sure. So okay, I cannot make 5 or 6, so I can discard that. But still, I can make these or these. I can make these, which is actually a very big number, because it is just, I just said, okay, for first group, these are all the possibilities. The same recursion will actually try on and will try for all other possibilities for success for the second group. So again, if I just take one of these, again, there were 1 2 3 4 5, like 1 2 3 4 5, but I say okay, there are 4 possible options for the first group, but let's say I take only 1 possible options and try to expand that further for that also. Okay, for the second group I can take either 1 or 2 or 3 like 4 I cannot take, because else I won't be getting any much space for the last one. So you saw again, for the second group I had 3 options, and for sure for the third group, which is last group, I just have the remaining part, which is this and this for the third group. So you saw that to just form the groups itself, we will actually form way many number of groups. So firstly, we have n elements, we have to form k groups. It's nothing but stars and bars. If you had seen the previous PNC problems, if you have not, just write on YouTube PNC by Aryan Mittal, you will get live stream videos and also the problem videos. Like mostly in the live streams, we have discussed the problem contest solutions, in which we have discussed about PNC problems. So in that we have discussed about stars and bars. Stars and bars is nothing but you just say that you have n balls, you have to place that n balls into k groups. So you will have to put k-1 partitions. Now with this k-1 partitions, I'll just say, okay, I have n-1 spaces and I have to place k-1 partitions into that. So that is how stars and bars work. But okay, we don't have to go deep into it. We just get to know, okay, the complexity will be in nearly about in factorial, or actually very high if we go and use stars and bars to go and get all the possible groups, all the possible combination of groups, because it can be way too many possible combination of groups. But if we go back and look, okay, for right now the minimum answer, as we saw, okay, first element will for sure come, as we saw, it will for sure come. If we take the second group starting with 2 and third group starting with 2, okay, this will be the answer as 5, minimum answer. And as you saw, I'll add in my score only the first value of the group, that's it. Okay, great. We saw that, okay, we cannot apply brute force, we have to think of something else. Now that something else is actually tricky, because the thing which will help us to think of something else is nothing but this distance. We remember, okay, we did not use this distance concept while we were trying to do brute force, right? It is the reason because we did not look into it. That's the most important part of this entire problem. This just one thing is the hands down most important part. How? Let's see. So we got to know one thing for sure, that okay, first element will for sure come. Now, one thing you have to realize that how the possible output can look like. So if I just go back and tell you a small example, with a small example, that how a possible output can look like, let's see. So basically, for the possible next range, as I said, okay, let's say one element will come with this. For the possible next range, I'll say that I can just do one thing, that okay, if I can try off and take something, and again, maybe I just said, okay, first group came in here, next group I am saying will come in here, because last group I know for sure can come in the end. So for this, I have these as options right now. So I know, okay, it is I1, it is ik-1. That I can assume. But right now, don't go into entirely deep into this, because we will not be using entirely much of this. We want to just figure out that how are these groups being formed and how are they impacting our answer. So I can just assume one thing, okay, I just wanted some number of groups so that every group should be able to at least form. For that group, now I will just derive that if I can get a range, I can form any group possible. So you that, okay, your answer was nothing but the first element of all these subarrays which you will take. It is nothing but your answer, final answer. This first element will for sure be nums of 0. These next elements are actually question marks for you, because this is what you were doubting about. Now I will say, okay, I will actually predict these values. How? Let's see. And not actually predict, but yeah, I'll just try it, because see, you want the answer to be minimum, and I am saying I will try to keep all of these minimum. A simple algebraic summation says, okay, if your result is minimum, if you're adding some values, positive values, so for sure you would want to have these values as minimum. So I am just about to now derive that, okay, I will be able to choose these values out, and I don't have to go and try for all the possible values. How? Let's right now imagine, okay, I have my first group. Again, the group size here is I have increased. So as to show you a bigger example, this is the, let's say, last group. This is the last group, which is the pink is the last group. This is the first group. It is the first, it is the last. It is the first, it is the last. Now I am saying I can now choose any value in between. Okay, first and last. For sure, two groups are formed, right? Two groups are formed. Remaining groups, I know, okay, like first group is there, this group is there. I'm just saying I can now form 5 groups. Like I just want to form 5 groups. Let's say 5 groups I want to form. 1, 2, 3, 4, 5. I am saying first and last group I formed for sure. Let's take it as 5. And I am now saying I can, for the remaining groups, I can choose any value whatsoever will give me the minimum. How? Let's say I just say, okay, I know that this value is minimum, this is minimum, this is minimum. If I know in between, in this entire array, I just wanted my summation to be minimum. For that, I need to make some groups. And for the group, I'll choose the first element. And I am saying, okay, I'll just choose this first element as minimum as possible. So I know, okay, these are the smallest 3 minimum values, because I know this is one group is formed here, one is formed here. So remaining, I have to form 3 groups. This means I have to choose the 3 smallest values. So I'll choose this as the smallest values. Now, I'll show you that I can ultimately backtrack and make the group itself. Okay, I can make one group like this so that he will form the first element. Next group I'll make like this, he will form the first element. Next group I'll make like this, he will form the first element. And the same way, for the next group, let's say if I just choose, okay, this was the array in between. Now I want the 3 minimum element. Now you might say, okay, Aryan, 3 minimum element are this, this and this. So for sure, I'll extend my first group. And for sure his value will remain as it is. So that second group can start from here, third group can start from here, fourth group can start from here. And what if I have something else also? No worries. If I just say these are the minimum values, then also I can just extend my first group and I can say my second group is like this, second group is like this, third is like this, and fourth is like this. So now I get to know, okay, I had to minimize my answer. First group, for sure, value will contribute nums of 0, which is constant, which we cannot change. For the remaining groups, I can just choose the minimum, k minus 1 minimum values for this, because I know I have k groups in total. This is constant. So I can choose k minus 1 minimum values. But remember, in this range, which was this, it is gone. Yeah, in this range of distance, because this distance is actually saying, okay, your index's difference should not go beyond this distance. So in this range, I just need to choose k minus 1 minimum values, and that's it. And that is the only part of intuition which is actually tricky to come up to. Now, when this portion is done, everything is very simple now. How? Because let's take the same example. Now, I'm saying that I will have, let's say, I will make the first group, for sure it will start off with this. For the next group, obviously for the next remaining k minus 1 groups, let's say my k was 6 back. So for the remaining 5 groups, right? For the remaining 5 groups, that need to be made from this entire range, from I1 to ik minus 1. And remember, my k, let's say my distance here is actually a 6. So you saw 7 minus 1. 7, I just took the entire range. What is the possible entire range? 7 minus 1 is actually 6. So for sure, I cannot go to 8, because 8 minus 1 will become a 7, which is more than my distance. So I cannot go beyond this range. I can be inside this range. So I know, okay, this is the range from which I need to choose k minus 1. Or let's reduce the k itself in the very beginning. So k is 5 now. Again, I have reduced the k because one group I will form from the very beginning. So one group is for sure gone. I have reduced my k. So remember, k is 6. I reduce my I reduce my k, and k now become 5, so that I don't have to do a k minus 1 again and again. Or if for understanding, I'll just tell you k minus 1 again and again, but in the code I'll just do a k minus minus. So in the very beginning itself. But here I'll just tell you k minus 1 again and again. No worries. So now I know this is the range. I need to choose. This is the range. I need to choose k minus 1 minimum elements in this range. Because I know for sure because I can easily form. If I just choose these, okay, one, let's say k minus 5, 1, 2, 3, 4, and let's say 5. If I choose these 5 as the minimum values, I know, okay, I can form one group here, one group here, one group here, one group here, one group here. No, last group I'll form the entire thing. That's I will for sure be able to form the groups, because I proved that above, that I will be able to form the groups. So I will know one thing, okay, my entire size, if the index is difference, okay, index is difference 7 minus 1, it's a 6. So the size of this array is actually a distance plus 1, right? That is obvious, okay. You will see 1, 2, 3, 4, 5, 6, and 7. We have 7 elements, while the difference is actually a 6, which you wanted. 7 minus 1 is the distance. So the length will be distance plus 1. which you have to check and bring out the k minus 1 smallest element. So I know my main aim, my maqsad is now that I will bring my minimum k minus 1 values in this entire range. Okay, that is simply how we can do it. Simply we can use a simple multi-set. But Aryan, you can also use a priority queue, right? True, but by a priority queue, I will have to make so many priority queues, because priority queue help us to remove only either the smallest element or the minimum element, like either the smallest or the largest element. And for the same way, like I want to remove maybe the smallest, maybe the largest, or maybe the any element I want to remove. I want to remove anything. We'll see why that is the use case, but you will want to remove some elements. But why in the first place you need any data structure, Aryan? Why can't you simply iterate on this entire array and get the minimum k minus 1 elements simply? No. Why? Because this is just the first range. You can also say, because here I considered that my starting element is only occupying just one value. What if the starting element occupies two values? Then you can start off with the next range. So you have to try on for all the possible ranges. It is just a sliding window. That is the reason. It's a sliding window. So that was robot dance. If it's a sliding window, then you know one thing. Oh, if it's a sliding window, and I know in the sliding window there's a concept that, okay, if you slide the window from here to here, then you just simply add this element, and this will be nothing but your, let's say, I minus x element. You will remove this element from what? From your data structure. What is your data structure? Your data structure says that in this range, I want the minimum k minus 1 elements, and for sure, which will actually same would have happened, which means in this range I would have kept track of minimum k minus 1 elements, and the remaining elements is, let's say, maximum, like remaining elements, let's say minimum elements, and let's say remaining elements. And the same way, when I'll slide down, I need to know from for this range what is again minimum k minus 1 elements, and again the remaining elements. So this is what I am concerned about, because I'm concerned about its sum. Its sum is actually my answer, and this is the sum which I'll slide the window, and minimum k minus 1 elements, that sum I have to minimize. Now let's see. Again, I'll do a proper diagram, but yeah, that is simply a hint that how we can go about this and what data structure we might end up needing, because we want minimum elements, we want sliding window, so we want operation of deletion insertion very fast. We want minimum maximum, so we want also that very fast. For that, the best data structure we have right now with us is a multi-set. Okay, so we can just have, okay, we will choose in this range. We saw the range size will be a distance plus 1. We will choose the minimum k minus 1 elements, and put that in a multi-set named as L. And the remaining elements, we can put it in R, saying, okay, L is the smaller elements, R is the larger elements, just for the naming convention. Now, okay, that is done, but you will slide the window, and that comes the interesting part. As you will slide the window, you will see that, okay, the current element which is new for you will be ith index, like ith element, and the element which should go out of your sliding window range should be I minus d minus 1, which is I minus distance minus 1. It should go out of your range. But you remembered, this was the existing window for you. And for that, you made your multiset L and multiset R. This is what you made. So one thing is for sure, if you made this specific thing up, so you have to make the specific thing for your new window also. But our window says, okay, I will not compute the entire thing again and again. So I have to again go and find the minimum k minus 1 elements in this new window. But I'll not do this specific step again. I'll use my existing window logic. How? I know that, okay, if some existing element is going, which is this I minus d minus 1 element is going, it can either go from the multiset L or multiset R. So I can just remove this element from either multiset L or multiset R depending upon wherever it is present. I'll simply remove this element. And for sure, what about the incoming element? For the incoming element, I know it should be inserted, but inserted where? I can insert this new element in my multiset L, but again, I can insert this new element in the multiset L depending upon it should actually go and be inserted, which means my multiset L stores the smallest k minus 1 values, right? That's great. So you can actually go and insert that. Okay, if let's say I have let's say existingly I have 2 and 3, and my R had, let's say, 4 and 5. Now I remove some element. Let's say I remove some element. I remove 3. But the new element which is nums of I, which is coming in as a 6. For sure, there's no even point to put this in my L, because for sure it's a very high value. So I'll put this in my multiset R. So I'll put it in 6. Now the multisets are imbalanced because for sure my L should contain k-1 elements. K-1 elements because I wanted k-1 minimum elements. So I'll just simply bring out the minimum elements from my multiset R to multiset L. I'll remove this and I'll push it back to a multiset L, and that's how I can shift my values in between the multiset. This and a similar kind of question, I forgot the question, I'll put it in the comments. A similar kind of question was actually asked by Google recently, and it had a very high frequency in last 6 months. I'll actually put this in the comment section, and it was a very frequent question. Like I saw that, and it had a very insane frequency in the last 6 months asked by Google. Now coming on back to this, and it was entirely based on priority queues and using multisets, like either priority queues or multisets. Again, I recommend multisets rather than priority queues, but it was either priority queues or multiset, and you want to have to just shuffle the elements between those two data structures, L and R, or basically left and right, or basically small and high. Now we just have to balance the disturbed size if the size gets disturbed after inserting or deleting some elements, because we know that this L should be having k-1 elements for sure, and remaining elements width should be inside my R, and we know that the sum of these elements, which means the number of these elements in the entire section will be nothing but distance plus 1. Now let's have a quick dry run of how can actually things happen with the example which is given to us. We know the distance is actually a 3, so for sure the first window which we will have is from I1 to like ik-1, which is 4 minus 1 is actually a 3. So you know the first window is this one, starting off with the index 1. Now I know if it's a first window, I have to grab the smallest k-1 elements and put it in L. Okay, I'll just iterate on this entire window. It's O of n time, and I'll simply push the smallest k-1 elements, which is the smallest 2 elements, because k is 3. First will for sure be answered as 1. So smallest, I want remaining 2 elements. So 2 elements, I'll put it in my L, which you will see 2 and 3. And for sure the remaining elements, I will keep putting in my R. So it is 4 and 6. Now, what is the current sum so far? Because for sure you have got one window in which you are saying, okay, you will choose these two minimum elements. So the windows which will be formed, right, the groups which will be formed right here will be first group, second group, and third group. This is the groups which will be formed. So for sure, what's the current answer? The current answer will be nothing but 1 will for sure be added, always added. So I'll simply add a 1, nums of 0, and for sure the current L size, L elements, like element sum, it is 2 plus 3. So 2 plus 3 is nothing but 5 plus nums of 0, which is actually 1. So my current sum is a 6. And it's just that I'll slide my window and minimize this answer, which is the current. Okay, cool. Now, but yeah, for the first combination, for the first window, my answer is right now 6. Now I will try to minimize that. I'll just shift my window out. Okay, this is the current element, which is new element. This is the element which should go out. I will simply remove this. Firstly, I'll just simply remove this. I will go and check, okay, it is actually inside my L. Oh yeah, simply remove this. If it's inside my L, simply remove this. But if it is also inside the R, no worries. We will handle that because we will balance it later on. No matter what we do right now, if it is in L, if it is also in R, no matter what, if it's, because it's a multiset. So no matter what, we will simply remove from one location only, but we will simply balance it later on. So no worries at all for anything. So now, okay, we have simply removed this, but simply we have to insert this also. So firstly, we will check if this element, if this incoming element, if it is more than my actual element, like actual element which is inside this, let's say inside like actual element which is maximum than the L. If it is more, if it is more, then I should actually be putting it inside my R. If it is equal or less, then I can put it inside my L. But right now, just to make you understand that, okay, how it can go in R, then how can all the shifting happens, let's take it as, okay, it is a high element. Let's say it is a 3. So it is more than the maximum element of L. My L is actually a multiset. It has many elements. So maximum element of L, it is, and I can just easily know maximum element of L because it's a multiset, and I can easily access minimum and maximum element in very small, like log n time. So I know one thing for sure, this 3 is more than the maximum element of the multiset. So for sure, I will not take any risk. I will I will put this in my R data structure. Now Aryan, why can't you put it in L? Because it could also have been a number as 7. Because if it would have been a 7, so okay, it's obvious that it will actually should go into R, and I should bring my 4 into my L. So that's the reason. I should always, if the value is more than the highest value of my L, then I should put this in my R. Okay, it was a 3 right here. I'll put this in my R. Okay, 3 is now in the multiset R. Okay, 3 is right now here. Now I'll simply have a check. Okay, now I think, okay, it is imbalanced. It is imbalanced. Again, whenever you are doing any operations, you saw that you deleted this. Simply remove from the current also. Current will keep on reading because you don't want to compute the answer again and again. Current will be actually handled simultaneously. Okay, great. Now we saw that, okay, our size is actually less. Now K is actually here, K minus 1, right? K minus 1. Because now why I have written K here? Because in the code itself, I will reduce K in the very beginning itself. So I can easily write K in the code. But here, because of your understanding, I was saying that I'll choose a K minus 1 because I know that in my multiset, I should have K minus 1 elements. So I know one thing for sure. I will grab the minimum element from here, which was actually 3, and then I will put it in my multiset L. So I'll put my 3 here. Although for the use case, the example was 2. So now for this, I added a 2. So I'll simply add a 2 in the existing value of current, and I'll simply get the new current. And I'll simply try to minimize this current every time because that's my answer. You remember, this is my answer. 6 is my answer. 6, this 3, this 5 is actually my answer. And if I just go and backtrack to show you that you just did what? You just tried to choose, okay, you just tried to choose this one, will for sure be chosen. You just tried to choose 2 minimum values. Here was a 2. So you try to choose 2 minimum values. So you are forming a group as this group, and this group. And that's how you got the answer. In just O of n log n time, because you are just using multisets. Let's quickly have a look at the code. I'll recommend, please code by yourself. But yeah, the code looks like we use 2 multisets L and R. Okay, that's great. Now, in the very beginning itself, I'm only concerned about K minus 1 elements. So I reduce my K in the very beginning itself so that I don't have to write K minus 1 again and again. Okay, now for sure in the very beginning, I told you my nums of 0 will for sure be added as a part of my sum. And I want to minimize my answer. Right? So I just did one thing. Okay, my current sum will for sure include my nums of 0. Now I go on to from I equal to 1. This is the first window. This is the first window of size distance plus 1. This is the first window of size distance plus 1. As I showed you earlier also, you will just put the values in your current sum and you will keep on inserting the values in your L multiset. But Aryan, you wanted only K elements, right? All the K is reduced. So you wanted only K minus 1 elements, right? Which is K is reduced. So yeah, make sure you only want now K elements. So, but you are inserting all elements. What the heck? Okay, no worries, because you will see that, okay, as my size is more than K, I will be keep on removing the elements and pushing that to a new set called as R. New multiset called as R. So here you will see that, okay, I'll reduce the value from the current because current is storing my sum. I'll add that value in my R multiset, which is the value which I am reducing. And again, I am reducing only the higher values from L. Smaller values will remain in L. I am pushing those higher values in R multiset. So it is for sure, okay, L will store the smaller values, R will store the larger values. And I will simply erase that specific element and make sure just do a find and then erase it, else you will end up erasing every frequency of like every element by that, because it's a multiset. So find the iterator to that element, which means just go the element, just do a find, so it will get the iterator of that maximum element in the L and then erase that element. And that's the power of multiset. Okay, now when this entire thing is done, you can simply go on and try for the next windows, starting from distance plus 1, distance plus 2 up to the super n, because you remembered if I just go back, this you remembered our distance was a 3. So this was the value distance plus 1. I will start off my next I from distance plus 2. So this is the thing which I have done here itself. I start from I from distance plus 2. Now simply remove the element which is gone, like which should go out of the window. So I'll remove I minus distance minus 1. If you remembered back, it is the element which is being removed is I minus distance minus 1. And then I'll simply add the new value. So firstly, it's the removing part. So I'll just check, okay, if that element which I am about to remove, which is I minus distance minus 1, if that is in L, if it is in L, okay, simply remove from the L, simply erase that from the L itself. And if you're erasing any element, make sure you also reduce the current simultaneously. But if it is in R, okay, simply erase in R, but you will not reduce the current because current is storing only the minimum value sum. Remember that. Okay, now I have reduced the key. I have just removed the n minus distance minus 1, sorry, I minus distance minus 1 element. Now for sure comes the insertion part. So I'll simply have a quick check. The element which I'm about to insert, if it is less than the maximum value in my multiset, in my L multiset, which is storing the minimum values, its maximum L is the multiset of minimum values. And out of those minimum values, what's the maximum value? If my nums of I is even smaller than that maximum value, for sure this element belongs to my L. So I'll simply insert that element nums of I in my L and also increase my current because current is for L, and else I can simply insert in my R. Now, okay, this is the simple insertion logic, but my multiset could get imbalanced. Now, what I mean by imbalanced is I am just concerned about L should be of size K. Like exactly, K is reduced, so it should be of size K minus 1. Remember that. So whenever I now say K, I actually mean K minus 1. So now my multiset should be of size L. Multiset should be of size K. If it is more, reduce it. If it is less, reduce it. If it is more, if it is less, increase it. If it is more, reduce it. So if it is less, which means, okay, my L size is less, I have lesser elements, and R has more number of elements, which means I should be having K elements here, actually mean K minus 1. So I should having K elements in this specific L. So for sure, bring the smaller elements from R and put it in L until your size becomes equal to K. So I'll just do the same thing. I'll just get the elements, smaller elements from R multiset. Smaller is nothing but R dot begin. I'll get the smaller elements. I'll push that in my L, and then I have to erase those elements from the R. And the same way, if my R has a bigger size, I'll get the higher elements from L, push it into R. If the L size is more, I'll get the higher elements from L and push it into R, and then erase from the L. And that's how, okay, now my entire L and R is actually balanced after this entire stuff. Okay, when this is done, simply update your answer with the current, because your current is being tortured on every removal, right? So that's the reason your current is being tortured. So current is actually showing the correct answer, the correct K minus 1 elements sum plus the first element, and for every window it is storing. So please update the answer with the minimum of the current value, and that's going to be the answer which you will return. Time will be O of n log n, and space will be O of distance, which is because you will store L and R multiset, and combiningly they will store, so like nothing but the distance number of elements, distance plus one number of elements to be more precise. And that's how you can simply solve this. I hope you got it. Bye, take care, bye bye. It was a very long question. Bye.